Starshades for ground-based telescopes. DART proved that asteroids share material. A new way to measure the age of the universe. And in Space Bites Plus, how Dyson spheres and stellar engines could be stable. All this and more in this week's Space Bites. So the next great challenge in finding exoplanets is that holy grail. We want to find an Earth-sized world orbiting around a sun-like star. The problem is that the stars are very bright and the planets are very faint. For us to be able to observe that Earth-sized world orbiting around a sun-like star within the habitable zone, the brightness difference is 10 billion to 1. And so you need to use a technique to hide the light from the star to reveal the fainter planet that is orbiting around it. Now, there are a couple of big ideas to do this. One is the coronagraph, and this is an internal device inside a telescope that takes the light, interferes it together, and allows you to null the light from the star and reveal fainter objects that are nearby. That gets you most of the way there. But another idea is a starshade, and this is where you fly a spacecraft designed to go directly in front of the star. It'll block the light from the star and it'll allow fainter planets that are around it to be revealed. And between the two of them, if you have the coronagraph and you have this starshade, you should be able to get to this place where you are completely blocking the light from the star. Then you can look at the planets. Then you can observe the atmospheres of the planet to see if there's life there. And we've seen this idea of the starshade for quite a while, and it's been proposed to fly alongside, say, the Habitable Worlds Observatory. But another idea that has been in the works for a while is instead of flying it with an existing mission, it could actually fly in orbit around the Earth and be used by various ground-based observatories. If you just sort of time the orbit of the starshade, have it fly above the observatories, then when it is passing along targets that they want, they can try and make their observations. But this is tricky because now you actually have this starshade that is going in orbit. And so it spends some amount of time in front of the targets that you want to be able to observe. So there is a new paper that has come out that has proposed that a starshade that would be 99 meters in diameter would be launched into space, and then it would be used by the Extremely Large Telescope and the Giant Magellan Telescope when they get built, and even the 30-meter telescope, which will theoretically be built in the Northern Hemisphere. And with this combination of these really powerful observatories, with this starshade floating out in space, then it should be able to detect and really categorize all of the planets in a solar system within just a couple of minutes. And it should allow the telescope to categorize the atmosphere of the planet in just a few hours. And so we could, with one relatively simple spacecraft, be able to turn ground-based super observatories into planet hunters. This idea has been around for a little while. It was actually awarded a NIAC grant a couple of years ago, and I interviewed John Mather, Nobel Prize winner John Mather, about this idea. Of course, he's the mind behind the James Webb Space Telescope, and sort of this is his new obsession. So I'll put a link in the show notes to that interview. Got a story about this from Lawrence Tugnetti. Speaking of coronagraphs, there's actually a problem with another spacecraft equipped with a coronagraph. I'm talking about the European Space Agency's Proba 3 satellite. And this is extremely cool. It has two spacecraft that fly in formation. One is the occulter, which essentially flies in front of the sun and blocks the light of the sun perfectly, so that it's kind of like a solar eclipse, but on demand and perfectly sized to block the light of the sun. And then there is a coronagraph, a second spacecraft that flies in formation with the occulter. And then back in February, there was a problem with the coronagraph spacecraft, which was causing it to change its direction and no longer be aligned with the occulter. And this also means that its solar panels were starting to move away from the sun. And this caused the spacecraft to have to go into an extremely low power mode. And now ESA is trying to recover the spacecraft. And sort of one idea that they have is to try and fly the occulter a little bit closer and try to get a look at how the spacecraft is doing. So right now it's no longer operational, and they're going to try to get it working again. And like, this is a great example of why this kind of formation flying is very tricky. Think about this. If you had a space telescope with that starshade, they're flying in formation. And then if either spacecraft is having problems, then the whole system doesn't work. But if you just have one free-floating Starshade, it's less moving parts. And you've already built the telescope. It's hard for a ground-based telescope to start drifting off axis. You've got bigger problems with your planet if there's something wrong with the telescope. In 2022, NASA's DART mission crashed into asteroid Dimorphos. And of course, this was us avenging the dinosaurs, demonstrating that we can change the orbit of an asteroid. And this impact noticeably changed how long it takes for Dimorphos, which is the moon, to go around this larger Didymos. But now researchers have looked at the last pictures that DART took moments before it slammed into Dimorphos, and they were able to see this strange pattern of rays across one hemisphere of this moon. In fact, this is evidence of a theory that people have had for a long time, that how you get moons in orbit around these rubble pile asteroids is that they're actually shed off of the asteroid. So there's a type of asteroid in the solar system called a rubble pile asteroid. And this is where there was once a more solid asteroid, two rocks smashed together, turned into this pile of debris that then collected back together because of its gravity. This is constantly under light pressure from the sun. It's heating it up, and that causes it to start to spin. It's this effect called the Yorp effect. The Yorp is named after the astronomers who proposed it. And as the asteroid starts to spin up, then it has very low escape velocity on its surface. And so rocks start to float away from the surface of the asteroid. And then they can collect into a moon that is going around the asteroid. And then over time, the asteroid and its moon are going to be changing the rate that they're spinning because of this Yorp effect. And so particles will be going from whichever one is spinning too quickly to the other one, sort of making it a little bit bigger, slowing it back down. And then this process seems to go back and forth. And so what DART saw was these series of rays coming off of the side of Dimorphos, and they weren't craters. And so that means that this material had to be moving very slowly. They estimate about 30 centimeters per second, so like walking speed. And the asteroids are a little over a kilometer apart as they orbit around each other. And so this material is just sort of slowly walking its way from asteroid to moon. And this was something that DART saw moments before it smashed into it, kind of like, I don't know, messed up the surface. So the European Space Agency's Hera mission is on its way to Dimorphos and Didymos right now and should reach them by the end of the year. And then we'll get much better images. And it won't be sort of seeing this in the last seconds before it's destroyed. It will be able to go into orbit and take a lot of observations and give us a lot more information. One other discovery that astronomers made was that the impact actually changed the orbit of the pair of asteroids, not just the speed that Dimorphos is going around Didymos, but actually just how the pair is moving through the solar system. It's not much, a little over 11 micrometers per second, but it's not nothing. And it shows, again, that we can theoretically move asteroids if we want to. We've got a story about this from Andy Thomaswick on Universe Today. How old is the universe? And this is a question that we have been wondering about for a long time. We know that the universe is expanding today. You just run the clock backwards so that one object that's on one side of us and the object on the other side of us were once at the same place. And that means you have to know the velocity. How quickly is the universe expanding? Once you know the speed that the universe is expanding, then you can run that clock backwards and find out how long it has been expanding for. And this is the Hubble constant, right? This is this measurement of the expansion rate of the universe. And there are two major ways that you measure this Hubble constant. One is that you measure it relatively nearby, where you are measuring objects like Cepheid variables or Type 1a supernova, things that are within a couple of billion light years of us, and you can measure that expansion rate. The other method is that you measure it in the cosmic microwave background radiation. How far is the cosmic microwave background radiation from us? And that will also help tell you how long the universe has been expanding. The problem is you get two different numbers. When you measure it relatively nearby, you get an estimate of about 13 billion years. When you measure it in the cosmic microwave background radiation, you get an estimate of about 13.8 billion years. So that is a gap of 800 million years. This is the Hubble tension. But I'm sort of stating it in a different way. We're talking about it not at the speed of the expansion, but in the age of expansion. The problem is that both of those measurements have been done with such precision that their error bars don't overlap. Astronomers are always looking for new ways to be able to do this. And now there's kind of a really cool way. And this idea has been proposed and done before, but now it's been done better than ever before. And that is that you look at stars, try to find a group of the oldest stars that you can, and then find the oldest. And then the oldest has got to give you a sense of how old the universe is. And so astronomers went through Gaia data, found a set of about 200,000 stars, winnowed that down to about 100 of the best candidates for stars that are very old, and then did very precise methods to calculate their age. And we've had a bit of a revolution in aging stars recently. You've got this new field called astroseismology, where you are able to measure fluctuations in the surfaces of the stars. That'll help tell you how old the stars are. But also you can look in places like globular clusters. They will help tell you how old various stars are. There's a lot of different methods to get at the age of stars. And if you want to learn more about astroseismology, I've got an interview here on the channel with Marc Hon. And when they sort of found all their candidate stars, looked through the oldest ones, and then calculated how old the universe would be based on that, the number is 13.6 billion years. So Cepheid variables tells you it's 13. Cosmic microwave background tells you it's 13.8. And the oldest stars that we can find tells you it's 13.6, which is kind of closer to the cosmic microwave background estimate. So is that the actual answer? Does that mean there's an error in the measurements to the Cepheid variables and the Type 1a supernova? We'll have to keep figuring this out. I've got a story about this from Mark Thompson. The Earth has auroras, and the way these work is that there is the solar wind coming from the sun. And the Earth has this magnetosphere. And as the particles of the solar wind reach the magnetosphere, most of them are deflected. That's why we are protected from the radiation from space. But some of them are trapped and go to the Earth's poles, which is where the magnetic field lines sort of connect up with the top of the planet. And so you get the particles going down the magnetic field lines, they pass into the atmosphere, and then they glow as they interact with the particles in the atmosphere. But the Earth isn't the only place in the solar system with auroras, and the most dramatic place that you can find them is at Jupiter. Now, Jupiter is not getting its auroras through the interactions with the solar wind in the way that the Earth does. Instead, it gets its auroras because of the moons from Jupiter. You can actually see the connection points in Jupiter's auroras where these magnetic field lines are connecting between Jupiter and Io and Europa. And in fact, we got some new images from James Webb that shows in infrared these spots in Jupiter's aurora, and these spots correspond to these connections between the moons, and they move as the moons are orbiting around Jupiter. We've got a story about this from Evan Goff. The sun looks like just this giant ball of glowing plasma that is rotating, but actually it has a differential rotation, which means that parts of the sun are rotating more quickly than other parts. So, for example, the equator takes 25 days. So if you pick a spot on the equator, it'll take 25 days for it to return back to its starting point. But at the poles, it takes 35 days for it to be able to complete one rotation around the sun. And it was believed that this is sort of a temporary phase, and that as the sun gets older, it should actually switch the rotation pattern. So the poles will rotate more quickly, the equator will rotate more slowly. And it's believed this happens because as the sun ages, it will just naturally rotate more slowly, just in general. As the star slows down, then it changes the turbulence inside the star, changes the magnetic fields, and then that would actually eventually sort of flip that behavior on its head. And so scientists in Japan took the largest supercomputer in the country, called the Fugaku, and simulated the interior of the star over billions of years. And what they found is that actually this process does not reverse, that it continues that same pattern of the equator going faster than the poles throughout its entire life. So it's interesting that, this sort of fundamental long-term nature of the sun's behavior, we were probably wrong about this. And then in fact, the sun will just continue on in this same pattern. And we should see a very similar behavior in other stars as well. I've got a story about this from Marc Hon. And speaking of the sun, we have been observing the sun for quite a while now, very carefully. And we know that the sun goes through this 11-year cycle, goes through its maximum and its minimum, where the polarity, like literally the magnetic field lines of the sun, flip. North pole becomes south pole becomes north pole. And astronomers have been watching these solar cycles and have made such careful observations over the last 4 solar cycles, cycle 21 through 25. And they've been able to measure oscillations on the surface of the sun that allow them to get a better sense of what's going on inside the star. Again, this idea of helioseismology, astroseismology. And they found that although these different cycles, the minimum points of each one of these cycles are similar, they are subtly different. And that each one almost has a fingerprint that then reverberates through the rest of the solar cycle. And this is really important because, us being able to predict the activity of the sun for the coming solar cycle is very important. It can disrupt our communications. We can have blackouts. We can have power disruptions. Really need to understand the sun better. And if we can see some kind of connection between how it behaves during that minimum point and then how it then proceeds on into much more activity, we can know whether it's going to be like a bad season on the sun. And we've got a story about this as well by Marc Hon. This was the Sun Week for Marc. Every week we do a vote on our channel where you tell us what you thought was the best space news story of the week. And the winner last week was a new radio map of the universe. So thank you everyone who voted. Now, as always, we will put the vote for this week's episode into the post tab here on our channel. It's there right now. So if you don't see it, you can just go into the post tab, vote for the story that you thought was the best. Now, if you don't see these in general, you should definitely be subscribed. Click on the notifications bell. Go into the post tab, vote for as many episodes as it takes for the YouTube algorithm to finally realize that you want to see this. So did you ever install SETI at home on your computer? This was great. I did it. I'm guessing half of you out there did this as well. This was like a screensaver that SETI researchers released that you could install on your computer. And then when your computer wasn't doing anything important, it could be analyzing SETI data, looking for signals from extraterrestrial civilizations. And so the astronomers who were doing this, they were looking at a region of the spectrum between 1.4 and 1.6 gigahertz. And this is known as the water hole. This is a place where you'd not expect a lot of normal signals, and this is where advanced civilizations would probably try to communicate in this gap in the spectrum. And so you've got this 200 megahertz chunk of the spectrum, and the researchers split that up into 1 hertz slices. And then they would send these slices out to people's SETI at home computers. They would run through the slice, and then if they found a signal, which I never found an alien, but then they would alert that to the researchers. And now it turns out that it's actually probably not that useful to try and look in those 1 hertz slices because the home star of the system has enough interference from just the plasma in the interplanetary region that it actually would distort the signals by 1 hertz, by 10 hertz, even by 100 hertz. And so if you're just analyzing a 1 hertz slice, then a signal could be varying through many different slices, and so would not appear as a distinct signal. So what's the solution? Well, the solution is more data. And so the researchers propose that you need to not just search in those really thin points, but also just collect more data, get more volunteers, more computers, and see if we can find those aliens. Got a story about this from Andy Thomaswick. Most galaxies have a supermassive black hole at their center, but there are occasionally ones that have two supermassive black holes where they are in the process of orbiting around each other and eventually merging. Now, we can see like very extreme versions of this where the supermassive black holes are very far away, but we just don't know if a black hole at the center of a galaxy is one supermassive black hole or two in orbit around each other. But now astronomers have developed a technique that they think will be able to figure that out. What you do is you look at the light that is nearby the center of the galaxy, and you're going to get gravitational lensing from the supermassive black hole. But if you've got two in orbit around each other, then you're going to get a periodic brightness, sort of a change in the brightness of the star that is being lensed by this supermassive black hole. Now, you have to do very long observations because remember, the black holes are moving, the stars in the galaxy are moving, we're moving. And so which star is being changed in brightness may sort of vary over time. And so you need a telescope that is probably going to be examining the sky for about 10 years, looking for periodic changes in brightness across many objects. So that's Vera Rubin. And so this is the kind of thing that Vera Rubin could be perfectly equipped and could actually turn up binary supermassive black holes at the hearts of galaxies. We've got a story about this from Dr. Brian Coberly. And finally, here is a cool image. And this is RCW36, which is about 2,300 light years away in the Vela constellation. This was seen by the Very Large Telescope, which is able to see into the infrared. And so in this image, you're peering through the gas and dust that is surrounding all these newly forming stars. And yet there's still so much material, so much dust that even in the infrared, you can't see through it. And the European Southern Observatory, who released this image, they call it the Cosmic Hawk Nebula. And I see it. I think I see what they're talking about, but it is a beautiful picture. Another example of a star forming region. Beautiful picture. Got a story about this from Matt Williams. I hope you're enjoying this week's episode of Space Bites. Got lots of great news here this week, but this is not our favorite place for you to be able to watch our episodes. And that's because YouTube really wants to put a lot of ads on it. Did you hear that now YouTube is making the ads unskippable on television? Yeah, this 30-second ads, you can't skip them. This is the direction this is always going to go. Now, there's a place you can watch our videos with no ads, and that is, of course, over on Patreon. We think the experience is so much better that we want to make a special version that has one additional story to tempt you, to taunt you, to go over and watch it over on Patreon. Completely for free. Don't have to pay, you don't have to sign up, but you get that version with no ads. And this week's bonus story is all about how Dyson spheres and stellar engines could be stable over long periods of time. I'll put a link in the show notes so you can go watch that episode. And of course, this is just a fraction of the stories that we were covering on Universe Today. And this is a really big week. The team has been very, very busy. Now you can go and follow all the stories over on the Universe Today website. But if you want a very convenient way to stay up to date, I write a weekly email newsletter that I send out every Friday. Contains write-ups of all of the stories that we're covering on Universe Today. Great pictures. I write every word. There's no ads. It's completely free. Go to universetoday.com/newsletter to sign up. Now, I've been complaining about YouTube and their ads, so I'm going to sort of restore the trust and give them a free advertisement. But first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrea Pedretti, Bear Lake Roofing, Brian Bodie, Caradwin, Chuck Hawkins, Commander Bieluk, Cooper Nelly, Dark Finga, David Giltonen, David Matz, Evan.pro, Greg Feely, James Clark, Janice Smith, Jeremy Mattern, Jim Burke, Jordan Young, Josh Schultz, Marcel Smits, Michael Purcell, Nordspace, OneStepForAnimals.org, Ren Kaidu, Richard Williams, Sean Sargent, Stephen Fallon Munley, Team 49, Telescope Scandal, Wolfgang Klotz, and Zeldaborg Galactic Defender, who support us at the Master of the Universe level, and all our patrons. All your support means universe to us. So I got an interesting comment from someone on YouTube. Archer Duchesne says, I've been a YouTube Premium member for many years, and the whole reason I joined was to get the ad-free content. I will never waste my precious time watching ads. I wonder how much of that premium membership goes to content creators. Probably zero. I watch a lot of YouTube videos. I appreciate the fact that many are thoughtful, intelligent, educational. If YouTube does decide to do this, I would leave the platform. Ads are insulting and degrading enough without being forced into them, whether premium subscribers want them or not. Defeats the purpose of paying for premium. So I am also a YouTube Premium subscriber. It costs $13.99 in Canada. I'm not sure what the US one is, and $22.99 for the family plan. And that's the one that I've gone for. So my whole family has YouTube Premium. And if I was to like strip away all of the services that I use, I would get rid of Netflix, I'd get rid of Prime Video, I'd get rid of Disney. Like the last one that I would be willing to lose is YouTube Premium. I can't deal with watching ads on YouTube. And so I totally get. And so the question you asked, like, is it good for YouTube content creators? It's great, actually. So we actually get about 40% of our revenue on the YouTube channel from YouTube Premium. And that's pretty significant. If everybody switched over to YouTube Premium, it would make a lot of creators able to just do this full time as their jobs and not have to take on other content sponsorships and put advertisements in their videos. We currently have the ability to not put any mid-roll ads into our videos, but I feel like it's just a matter of time before they decide to take over to help me deal with that. I mean, they're already making as many suggestions as they can on places I should be putting more mid-rolls in, encouraging me to turn on mid-rolls. They really want me to put on mid-roll ads, and I refuse to do it, but I know it's just a matter of time before we have to. And so like the way YouTube Premium works is that they take sort of all the watch time that you have, they take the revenue that you're paying them as a premium member, and then they split that up among all of the creators on who you watch. And so it's this really direct connection between what you watch and who gets revenue from your watch time. I'm sure it sounds like it's not very much, like you only watched 10 minutes here, an hour there, and yet that revenue that you pass along to the creators is much larger than the amount that they make from ads. In many cases, creators will make, say, $2 for every 1,000 ads that they display to someone who watches their stuff. So it is both, I think, the most effective way to watch YouTube, and it is the best way to support the creators that you like, especially the ones who've made giant 10-hour videos that you could watch on repeat. So you're welcome, YouTube, for that free ad. Thanks, everyone. We'll see you next week.